student from National Technical Senior High School, and we are curious about how a pouring paper airplane would fly in gravity. In our experiment, a controllable variable includes the angle between the wings and the horizontally flat, as well as the fuselage angle and the whether tilted upward or downward. After conducting experiment, on Earth and collecting data, we've identified the 5 best throwing factors: throwing vertically downward, throwing horizontally, throwing diagonally downward, throwing with the wing at a 45-degree angle to the ground, and throwing with the wing perpendicular to the ground. In our gravity experiment design, this move will be repeated 5 times, and after release, the airplane will not land as speed as on Earth. Instead, we will observe these 5 paths for 10 seconds and compare this observation with our Earth gas data.
Let me introduce our experiment, the design and the various to those given to astronauts. From our observation, we identified 2 main flight paths: vertical circular motion, shown in these videos, horizontal circular motion, as seen here. Now, let's look at the average and standard deviation from 15 trials. In general, longer rotation time suggests larger radii. Statistically, vertical circular motion takes longer than horizontal ones. For specific throwing, horizontal throwing struggles. Vertical throwing, because it is more affected by gravity. Vertical throwing is quicker than horizontal and diagonal throwing. For success rate, horizontal throwing struggles due to their sensitivity to small angle change. They also face greater gravitational resistance at release, leading to more failures and errors. Throwing upward is difficult on Earth. Collecting data is hard, so we didn't include it as a factor in the experiment.
A bit about the flight results of the pouring paper airplane, which are closely related to the Coanda effect. Simply put, air tends to follow the curve of the airplane's wings without easy separating. Next, the angle of attack. The wings of the airplane's wings are slightly tilted upward. This allows air to flow more smoothly, reducing drag and helping the airplane fly more steadily. Finally, the lift. The Coanda effect causes the wings to push air downward, which creates an upward reactive force. This picture shows the forces acting on paper airplane on Earth, primarily influenced by 4 forces: lift, gravity, thrust, and drag. And this picture shows the forces acting on paper airplane in microgravity. Here is almost no gravity, so lift no longer needs to counter gravity to maintain flight. As a result, lift increases.
And next, I will summarize our experiment and explain our hypothesis. When soaring vertically downward, the airplane will fly in a shrinking circular path due to air resistance. Soaring horizontally, the flight path is similar to the vertical thrust but is not in a horizontal direction. Soaring diagonally downward at the angle, the airplane also follows a circular path, usually smaller when soaring horizontally. And 45-degree thrust, the airplane will spiral upward instead because there is no gravity. And soaring with the perpendicular, it will fly in a circular path parallel to the ground. In the right picture, thrust and resistance balance out, maintaining the circle size. And thank you for listening.